So we've introduced the concepts of sources and sinks, which allows us to take data from one place and pour it into another place. However, generally, we don't just want to take data from one place and move it to another place. We usually want to perform some sort of transformations along the way, and those transformations can be largely varied depending on what we're trying to achieve. So we need a way to take that data and transform it in some way, and that's where flows come into play. So a flow is a graph stage with a single input and a single output. So this is almost like a combination of our previous two box diagrams here. We see the input pipe and the output pipe. You'll also note the color change. So in the original source diagram, it was drawn as blue and the sink was drawn as pink. Now we actually have a color change going from blue to pink, which in our little diagram is basically indicating that a transformation is taking place here. Again, thinking about this from the plumbing perspective, our flows in this case is the actual pipes. So we have a pump, and that is pumping water. And we have a sink, which is where the water is being pumped to. But usually you don't just connect the pump directly to the sink. Usually you would have some sort of plumbing pipes in between, which might change the direction of the water, or it might widen or narrow the flow in order to produce a change in pressure. So those are all possibilities. And so that's essentially what our flow is doing, is it's providing the pipes that will take the data from one place, put it in another place, and transform it along the way. So they're used to move data from a source to a sink, manipulating that data in some way, like transforming it or filtering it. A flow acts as both a source and a sink, obeying the rules for both. We define a flow as a flow with three type parameters: an input type, an output type, and a materialized value. So again, the input type is the elements coming into the flow, and the output type is the type of the elements going out of the flow. So they might change. They might stay the same, but they might change. So a flow receives demand from downstream and propagates it upstream. So when demand comes into the flow, then the flow has to send that demand upstream. But like with a source, if there is no demand, then the flow must stop. So it's possible that the flow will have already had data pushed to it from upstream, and now it has to theoretically push that data downstream, but the downstream may not have signaled demand yet, and so the flow will have to hold on to that data until the downstream is ready for it. Now, of course, if the flow has a small buffer that it can use to hold that data, and the buffer fills up, then the flow might have to stop signaling demand upstream so that the sink can stop, or sorry, the source can stop pushing to the flow. So the flow then can create its own back pressure to prevent itself from overflowing buffers and such. So flows can propagate back pressure upstream by reducing or stopping demand. Alternatively, you can create flows that will just drop data, or they will buffer data, or whatever. So the flow can actually potentially make a decision as well about what to do with that data if there's no demand. So a flow is both a consumer and a producer. It uses the message flow of both source and sink, so it can respond to both on-push and on-pull handlers, and it can do that using the same sort of messages as a source and a sink. So we have flows to map elements. This is probably the most common flow that you'll see. We have a map which will transform the stream by applying the given function to each element. So in this case, we have a flow of integer not used. This is basically a flow which takes integers, produces integers, and we don't worry about the materialized value. And we've named it double because all it does is take the incoming integer and multiply it by 2. So it's just doubling the value of that integer. We can also use a map async, which accepts a function that returns a future, but still guarantees ordering. So here in our example, we've just taken our double, and we've, instead of returning the value times 2, we return a future of the value times 2. And what that does is that it executes that asynchronously. We provide a parallelism value here. In this case, we've set it equal to 4. And this defines the amount of parallelism used to resolve futures. So with a value of 4, it basically means we can have 4 futures resolving simultaneously before we have to start creating back pressure. We have map async unordered. In this case, what it does is where map async will preserve the ordering, map async unordered does not. So whichever future returns first is going to be the first one that gets emitted. We have flows to flatten elements. So for example, we have a map concat. And what that's going to do is it's going to transform data into a collection that is flattened into the stream. This is similar to a flat map on a collection. We don't call it flat map because if you call flat map on a collection, you're taking a collection of collections and flattening that. In this case, we don't have a collection of collections. We have a stream of collections or a source of collections. And so it's not quite a flat map, which is why we call it map concat instead. So we have flows to group elements. We can group elements into fixed size batches. In the first example, we're grouping into groups of 10 elements each. And this will produce a sequence of whatever the element type is. So in our case, the element type was int. So we produce a sequence of int where each sequence will contain 10 elements. We can have a sliding window of 10. This creates a sliding window over the elements of the stream. So again, it's producing a sequence. But in this case, where the first one, if we were to group the numbers from 1 to 100, then we would get 1 to 10, and then 11 to 20, and then 21 to 30, etc. In the second case, what we would get is 1 to 10, and then 2 to 11, and 3 to 12, etc. And that's because we've set a step value of 2. We could adjust the step value to change how that window behaves. So we have stateful flows. Fold, again, this is much like the fold that we've talked about with the sinks. We're using it for the same purpose here. We're computing a sum. It allows a stateful transformation by passing previous state into the next iteration. One thing of importance here is that a fold will only emit the result when the upstream completes. So this is just going to pull everything in and compute it in memory, but it's not going to send anything downstream until the upstream has completed, and then it will send the final result downstream. Accumulate is different. It works in a similar manner where it has stateful transformations passing previous state to the next iteration, but it will the scan will actually emit each new completed result. So here we have accumulate and we have flow.scan, and it's actually going to emit each result as it computes it. And then obviously if the upstream terminates, then it will emit a final value. But if you want to keep track of that accumulating value, you can do that in your sink or downstream. We have flows to filter elements. So filter will filter elements in or out of the stream. And then we also have collect, which is a little different. What it actually does is it applies a partial function to elements in the stream. Matched elements are transformed by the function, and unmatched elements are dropped. So it's both transforming and filtering at the same time, essentially. So in the first example, we're just producing odd numbers, and we're just taking whatever our incoming integer is, computing the mod of 2, and checking if that equals 1, and that will produce odd numbers. In the second example, we do a very trivial thing with a collect to produce even numbers. We have our partial function, so we check if x mod 2 equals 0, then we return x. Otherwise, we return nothing, we ignore it, in which case it will get filtered out. We have flows to limit elements by time. So take within, in our first example here, we have take within 1 second. This will produce 1 second of data and then terminate. We have skip 1 second of data using a drop within. So what that's going to do, we have drop within 1 second. So what it will do is it will drop the first second of data and take everything after that. We have group by second in our third example, and this is using a grouped within. And what it does is it takes two parameters. So the first parameter is the size of the groups, the maximum size of the groups. And then the second parameter is the maximum amount of time for the groups. So what it's going to do is it's going to group according to whichever comes first. So if it pulls 10 elements before a second has elapsed, then you'll get a group of 10 elements. If it pulls a second of data before it gets to 10 elements, then it will produce a second of data in a sequence of integers in this case. We have flows to combine sources. So here we are zipping, and this will combine the incoming elements with elements from another source. The result is emitted as a tuple of both values. Now this is tricky here because this is actually not a linear stream anymore. We're actually taking two streams and kind of combining them together. So we're doing, this is almost like a shortcut to using graphs, which we'll talk about later, but using kind of a simpler API. It's also important to remember this one because we'll use this one in the exercises fairly heavily. So here what we're doing is we're doing a zip with index. So we have a source from iterator, and it's basically just taking an iterator from 0, so it's going to produce just numbers from 0 and up. And it's going to zip that with whatever the incoming string happens to be. And so essentially we'll get tuples of the index and the element. We have flat map concat. This is similar to map concat, but it operates on sources rather than iterables. So this is more like a true flat map, which is why we've called it flat map concat. Now, we do have to differentiate here between flat map concat and flat map merge because they are different behaviors. So flat map concat is going to transform data into a collection that is flattened, into a source that is flattened into the stream. Substreams are consumed in sequence, which preserves ordering. Flat map merge, on the other hand, is like map concat, but substreams are consumed simultaneously, therefore your order is not guaranteed. And with a flat map merge, you provide a breadth value, which indicates how many substreams to consume at a time. Keep in mind that with flat map concat, if the source never terminates, then you will never move on to the next source. So keep that in mind because that can be relevant. Similar with flat map merge, if you have enough sources that never terminate, then you can end up in a similar situation. But as long as there is less than whatever that breadth value is, you can always move on to another one. We have flows to buffer elements. So here we have the buffer flow, and we set a buffer size as well as an overflow strategy. And what this will do is it will buffer elements in memory until the downstream is ready to receive them. Now, there are different values for the overflow strategy. You can specify back pressure, and what that will do is when the buffer fills up, then it will apply normal back pressure. You can say drop head, which will drop the oldest element in the buffer to make room for new elements. We can drop tail, which will drop the newest element in the buffer to make room for new elements. We can drop new, which will drop the new element coming in, leaving the buffer unchanged. We can drop the entire buffer, which drops all elements in the buffer to make room for new elements. And then we can also just choose to fail. So if the buffer gets full, we just fail and complete the stream. So that's another option. Going back to our previous example of using these overflow strategies, that was in the source.actorref. Be aware that the source.actorref will not accept a overflow strategy of back pressure because you have no way to provide back pressure in the case of an actor. So we have flows for slow consumers and producers. Here we have an expand. This extrapolates additional values from the incoming elements to fill gaps when the consumer is faster than the producer. So in this case, we actually have a fast consumer and a slow producer. And what it will do is it will apply a function that takes whatever the previous element is and produces a new element using that function. So an example of this would be if you're producing a graph or something like that, and your previous element was 5, then your function may just say, take whatever my previous element was, which happened to be 5, and return it again. And so your function might actually be an identity function. And the result would be, it will just continue to produce that value of 5 until the producer comes up with a new value. On the other hand, you might actually extrapolate something from that. So you might be able to look at previous values and say, well, the previous value was 5, and therefore I know that the next value will be maybe 6. So I'm going to do, previous value plus 1, and I'm going to produce that instead. So you might be able to extrapolate data from whatever the previous value was. We can do a batch. This will group elements into a batch to be consumed downstream if the producer is faster than the consumer. A good example of this would be if you're writing to a database. Oftentimes it's faster to write multiple elements rather than to write them individually. You can batch them up on the database side into a single transaction, and that can be faster. So in that sort of situation, we can actually leverage this, and what this will do is it will batch those elements as long as the downstream is not ready to receive more demand, and then when the downstream is ready, it will send the whole batch. Now, on the other hand, if the downstream is keeping up just fine, then what this will do is it will just send one element at a time along. We have conflate, which creates a summary of multiple elements to be consumed downstream if the producer is faster than the consumer. An example here would be if we were trying to compute a sum downstream. So we have a bunch of integers coming in and we're just adding them together, but for some reason our downstream is slow. What we could do upstream is we could conflate the values so that as each integer comes in, we can say, well, the downstream's not ready to receive this new integer yet, so I'm just going to compute a sum of my current integer and whatever the next integer that comes in is. And then when the downstream is ready, I will just pass it the sum. So because we know that whether we compute the sum downstream or whether we compute it upstream, the result is going to end up being the same. We can leverage that using conflate. Obviously, that's a very simplistic example, but hopefully it's one that helps you understand the nature of conflate. We have flows to log elements. So here we write the elements in the stream to a log while passing them to the next stage. A provided name is included in each log statement. So in this case, we've passed just name, and so each log statement will include that string so that it's easier to find. Optionally, you can provide an extract function that will extract information from the element, and only the extracted information will be logged. So normally what it does is it just calls the toString, but that may be insufficient. We may want to only look at pieces of whatever the element are, and so we can use that extract function for that. It requires an implicit logging adapter to use, and by default elements are logged at a debug level, but that can be configured using with attributes, and we'll talk more about with attributes later. So there are also some convenience methods on source. Basically, for convenience, all of these transformations that we've talked about are available directly on a source as well as on a flow. That means that rather than having to create a flow, you can just call source 1 to 10.map, and that will actually apply a flow which does the mapping for you. You can do .filter, conflate, whatever on these sources. One note, however, is that when you do this, what you get back is a new source with that transformation applied. Okay, so let's look at an exercise. So you can see the sections in red again are what we're going to implement. Sections in green are what we've already done, and then gray we haven't done yet. So here what we're going to do is we're going to have a a flow that will paint our unfinished cars. So that's actually going to take our colors and combine them with the incoming unfinished car, and then paint, as a result, it will paint the car. We're going to have a couple of things happening in Engine Shop. We're going to take our shipments and we're going to produce a flow. Instead of having shipments, we're going to produce a source of engines. So right now we have a source of shipments. We need to transform that into a source of engines. Then we are going to take those engines and again combine them with the incoming unfinished car and produce a result there. And then we are going to do a similar thing with our wheels, but we just have to be a little more aware with our wheels, because with our wheels, we're actually not going to take individual wheels. We actually want groups of 4 wheels, so we have to do something there. And then we're going to have an inspection flow in our quality assurance, and what that will do is it will take our unfinished car and it will inspect it to ensure that it meets the necessary criteria, and if it does, it will produce a car out the other side. So we will assemble our cars. We will create a variety of flows that add our components into our cars in order to move them towards a completed state. So let's go ahead and work on that exercise.